Welcome back to Applied Physics Lecture Series, Unit 4 Lasers, Lecture 2 Einstein's Coefficients and Importance of Einstein's Theory of Radiation. What is this Einstein's Theory of Radiation? First of all, you have to know the importance of this Einstein's Theory of Radiation. In the year 1917, Einstein proposed his Einstein's Theory of Radiation, so in which if you operate the two process like absorption and emission process in a systematic way and in a sequential manner, always there is a possibility to produce a new kind of electromagnetic radiation. And the second point in this Einstein's theory of radiation is, out of the two process, absorption and emission, the role of emission, particularly the role of stimulated emission, is very crucial to produce a new kind of electromagnetic radiation. So with help of these two assumptions, he made a mathematical relation, and he identified the use of the emission coefficient rather than absorption coefficient. So briefly, this theory is known as Einstein's theory of radiation or Einstein's coefficients. And the important point is, exactly by implementing this Einstein's theory of radiation in the year 1960, Myman is the scientist who succeeded to operate the first successful laser, which is nothing but ruby laser. Exactly implementing the Einstein's theory of radiation or Einstein's coefficients mathematical relation, Myman succeeded to operate the first successful laser, that is ruby laser. That means nearly after 4 decades of proposing this Einstein's theory of radiation, we can able to operate the actual laser. That means the laser came into the picture. So that is the importance of Einstein's theory of radiation. Now let us see briefly what about this Einstein's coefficients or Einstein's theory of radiation. So in a collection of atoms, usually material which is made up of atoms, in such atoms which are present in a material, usually the 3 transition process takes place simultaneously. Those 3 transition processes are, one is absorption, it is also known as stimulated absorption. Usually it will take place in the upward direction, that means from ground state to higher energy levels. And second one is spontaneous emission. It will take place in the downward direction, that means once absorption is over, it will take place from higher energy level to lower energy level. And third one is stimulated emission. It is also a downward transition. It also takes place from higher energy level to lower energy level once the process of absorption is over. Now we have to see briefly what is meant by this absorption, spontaneous emission and stimulated emission process. First of all, we will see what is meant by absorption or stimulated emission. Usually, under normal circumstances, majority of the electrons are present in the ground state. So the electrons which are present in the ground state are excited with certain amount of external agency. As a result, the electrons which are present in the ground state are absorbing certain amount of energy from the external agency, and they are raised to the higher energy levels. This process is called as absorption. Physically, we are giving certain amount of energy by external means to the electrons present in the ground state or lower energy level. As a result, they will absorb energy which is equivalent to photon amount of energy. Thereby, they will be raised to the higher energy levels. That means now once absorption process is over, majority of the electrons are present at higher energy level. This is known as absorption process. Then coming to the spontaneous emission. Once absorption is over, the electrons which are present in the higher energy level are returned back to the ground state on their own without any external agency, spontaneously, by releasing one photon amount of energy. Such a process is called as spontaneous emission. Usually spontaneous emission process takes place once the lifetime of electrons in the higher energy level is over. Then stimulated emission. This is also takes place once the absorption is over. The electrons which are present in the higher energy level are returned back to the ground state forcefully with influence of certain amount of external agency. That means you have to give certain amount of external energy to start the process of stimulation. As a result, the electrons which are present in the higher energy level are returned back to the ground state by releasing photon amount of energy. Such a process is called as stimulated emission. And the major difference between the two emission processes is, during the spontaneous emission process, always we will get incoherent photons. During the process of stimulated emission, we will get coherent photons. And if you consider N1 as the number of atoms present per unit volume with energy E1, that means the number of electrons which are present in the ground state are represented with N1, and such a ground state is having an energy E1. Similarly, N2 is the number of atoms present per unit volume in the higher energy level and which is having an energy E2. And U nu is nothing but energy density of the interacting photons. That means when these photons interact with atoms in both upward and downward directions respectively, both upward and downward, absorption process and emission process. And during the upward transition, that means during the absorption process, stimulated absorption rate is N1 U nu B12. What is N1? The number of electrons present in the ground state. U nu is nothing but how much amount of external energy you are going to give to the electrons. B12 is nothing but usually the process of absorption takes place from state 1 to state 2. Here B12 represents Einstein coefficient for the absorption process. And downward transition. Downward takes place in two ways during the process of spontaneous emission and stimulated emission. So during the downward transition, if it takes place through spontaneous emission rate is nothing but simply N2 A21. Here N2 is the number of electrons present in the higher energy level. Usually the process of emission takes place from higher energy level to lower energy level. That's why A21. This is the process takes place from state to state 1. And you know very well, spontaneous emission doesn't need any external agency. That's why N2, A21. So here A21 is nothing but Einstein coefficient for spontaneous emission. Similarly, if you consider another downward transition, which is nothing but stimulated emission. Here the stimulated rate is nothing but again N2, B21. Now we have to add again U nu. Here U nu is nothing but external source of energy. Here to conduct the process of stimulated emission, we have to give external amount of energy. And N2 is the number of electrons present in the higher energy level. And B21, 21 is nothing but the process of stimulated emission also takes place from higher energy level to lower energy level, and its Einstein coefficient is represented with B21. Under thermal equilibrium, so equilibrium means number of transitions must be takes place in the same number. That means under the thermal equilibrium, the number of upward transitions must be equals to number of downward transitions. That means how many number of electrons are excited during the upward transition. That means absorption must be equals to how many number of electrons are returned back during the process of emission. That is a downward transition. Then you have to equate the two equations. So that is N2 A21 plus N2 U nu B21 is equals to N1 U nu B12. And taking U nu as a separate component, then we will get A21 by A21 N2 by B12 N1 minus B21 N2. Dividing by both the numerator and denominator with B21 N2, then you will get U nu is equals to A21 by B21 into 1 by B12 N1 by B21 N2 minus 1. By substituting N1 by N2 as exponential of HU by QT, this is nothing but Boltzmann distribution formula. We will get the formula, you will get the expression for U nu is nothing but A21 by B21 into 1 by B12 divided by B21 exponential of HU by KT minus 1. Here B12 and B21 are same. B12 is nothing but Einstein coefficient for absorption. B21 is nothing but Einstein coefficient for stimulated emission. Both are having same energy. That's why by equating B12 is equals to B21, and we are comparing the above equation with Planck's energy distribution radiation formula, which is nothing but U nu is equals to H pi 8 pi H nu cube by C cube into 1 by exponential of H nu by KT minus 1. Then comparing the equations, one is from Einstein's formula and second one is Planck's energy distribution radiation law. We will get A21 by B21 is equals to 8 pi H nu cube by C cube. Here the two coefficients A21, B12 and B21 are known as Einstein's coefficients. Observe the last formula, Einstein's coefficients A21 by B21, which is equals to 8 pi H nu cube by C cube. Here there is no term which is representing absorption. B12 is the absorption coefficient given by the Einstein. The term is not there. That means in order to get a new kind of electromagnetic radiation, the role of emission is much more important than absorption. Thanks for watching.